Hey, my name is Adrien and I focused on error analysis and C coding.
My name is Baptiste and I'm a code designer and developer.
My name is Irlon and I'm presentation and video in charge.
My name is Navneet and I am the project manager and MATLAB developer for this project.
I am Raees and I was involved in developing the positioning algorithm of our implementation.
My name is Yuqi and I'm a state developer.
We're the Blue Group and our project name is spirals-based positioning. The goal of the project is to create a positioning system with centimeters precision. The basic idea is to use 3 or more fixed base stations called anchors in specific places of the room. When acquiring the distance from this anchor to mobile stations called tags, we will calculate its position. The devices used are evaluation boards from DecoWare.
In our ranging system, we implemented 2 algorithms, two-way ranging and thematic two-way ranging. For two-way ranging algorithm, it is quite straightforward. First, tag sends the pull message to anchor to initialize the distance measurement. After anchor receives this pull message, it waits for a certain delay time period, which is known both by tag and anchor side, then sends back a response message to tag. By the time tag receives this response message, it has enough information to calculate time of flight.
So, as Yuqi explained, the two-way ranging is a very simple algorithm, a very nice algorithm. But it has a really strong dependency on the oscillator frequency. To reduce these dependencies and these errors brought by these dependencies, we decided to create a new algorithm. This algorithm is called the symmetric two-way ranging, and it leads to less errors linked to the clock. The main difference between these algorithms is like we also send a poll message, then wait and send a response message, but there we wait another time on the tag side to send the final message. This final message has more timestamps and it facilitates the calculation of the time of flight on the anchor side. Once the final message is received by the anchor, it is computed and sent back to the tag in the next ranging round. This leads to less errors, and for such it's more appropriate for our applications.
We estimate the position of the tag by using the distances of the tag from 3 anchors whose positions are known. We create 3 spheres having the distances as the radius and centered around the 3 anchors, and the position will be the intersection of these spheres. However, these distances measurements used in our implementation have noise, and we use techniques in estimation theory to remove the effect of this noise.
The system has been presented as it should ideally work. Now, I'm going to explain what could possibly go wrong in the ranging experiments. There are 2 main sources of error. One of them is rooted in the clock system of each antenna. Indeed, each anchor should wait a very specific time and respond, so a tiny bias in clock crystal frequency will have a crucial influence in the ranging. Other errors are caused by disturbances in the very environment where each antenna are communicating. It can be due to the presence of a wall, of a board, or computer. So we have performed clock calibration and bias correction in order to curb the influence of all these issues.
Let us show you a live demonstration of the prototype we developed. The user interface has a plotting area with a route mapped for our reference and some options for configuring the system. Once we start, the position of the tag is shown by a black marker and the path traversed with red dotted lines. As you can see, I'm moving around the room with the tag, and the corresponding position is tracked with significant accuracy compared to the reference route in the plot. In this project, we studied and developed the communication protocols between a fixed anchor and a moving tag. We also studied various methods for estimating position and implemented recursive Gauss-Newton method for static and extended Kalman filters for dynamic positioning. Study and analysis of the sources of error contributed immensely in mitigating the bias errors in our measurements. We carried out experiments to calculate the CPU clock ticks and range measurements at various locations in the room. It helped us understand the effect of environmental factors on the bias errors and the relative bias between different pairs of antennas. Final result from this study is a heat map of bias correction values which we use to calibrate the range measurements during the real-time implementation. We designed a user interface to configure and run positioning system. The system can be calibrated for any room with 3 or 5 fixed anchors. We obtain the range measurements from fixed anchors and apply bias correction on them. An estimate of the position is calculated by positioning algorithm in MATLAB with a mean error of around 10 centimeters. This was precisely the goal of our project. Thank you.